All right, and so now for anyone who is studying mathematics with me, after you have hopefully become fluent with with how to operate with polar coordinates, then now we are ready to get into that exciting world of polar equations and as well as polar curves here. Okay, and so let's now have a brief understanding or to have a solid understanding of what polar equations are all about. So in your understanding in math up to this point, in your learning up to this point in math, then an equation that you used to know relating the two variables x and y, okay, like say this one here, x squared plus y squared equals 5, okay. An equation like this is an equation in terms of two variables x and y, okay, and then this equations here are the x and y are intended to be the variable representing the horizontal coordinates, and the y here is the variable intended to represent the vertical coordinates. So this equation here is a rectangular equation, or more precisely we call that, this is a Cartesian equation, okay, because now, well, on the other side of this, I'm talking about any equation has a graph. Any equation has a graph. So we're briefly looking back at those equations we've been knowing. So an equation like this relating the two traditional variables x and y are here, and most of the times they are like that. Then these are regarded as the Cartesian equations. But what it does here is that an equation, general rule of thumb, any equation points out a relationship between your two variables in the equation. So this equation here has two variables. An equation can even have more variables, a lot more variables. But here let's just route our case down to only two variables for now. And so this equation by far points out a relationship between the two variables. There's the variable x and there's the variable y. So the point now is that whatever values we assign for the two variables here, x and y, they have to maintain this relationship being x squared plus y squared equals 5. Okay, and then I call this Cartesian equations. Now, as a real clarification, an equation like this is usually regarded as a Cartesian equation simply because the x and y variables here are intended to represent horizontal coordinates and vertical coordinates in rectangular coordinates, okay, and so and it's a tradition, and so now, and then specifically for this equation, any equation in math, any equation has a graph, and so we can graph this equation and come up with a graph that appears to be a circle, and that circle center at 0, 0, with radius being square root of 5. That's what this equation gives us. So again, generally as a rule of thumb right here, any equation, okay, has a graph. So an equation points out the relationship between the two or more variables, and then any equation has a graph. And then for our case right here, we're specifically focusing on equations with two variables. And so the one I've been briefing through right here is the equation that's where the two variables are intended to represent Cartesian coordinates. Okay, so x is for the horizontal coordinates and y is the vertical coordinates. And that's for that reason the graph appears as following. And every point here has an x and y rectangular coordinates. That the x and y coordinates on this equation, on this circle, has to satisfy this equation. And so that's the general fundamental about the equation, any equation. Okay. And so now once we recall for ourselves the true meaning of an equation, then we are ready to step over to the world of polar equation. So after you have learned generally about what polar coordinates are all about and how to operate fluently, hopefully at this point, how to operate fluently with polar coordinates, then the two main variables being involved in any time that you are working with polar coordinates is the radius and the theta. Okay, the two mains, and pretty much anytime we're working with polar coordinates, the only two variables we ever have to be working with is the radius as lowercase r and theta as as the other variable. Okay, and that's for the angle from the, according to the understanding we have had up to this point right here. This is how much angle our point made with the x-axis. It could be positive, it could be negative, or it can also be positive, it can also be negative. All right, and so now polar equation again. So now we have two variables. So a polar equation is an equation that at least, is an equation that points out a relationship on these two, specifically on these two variables, the radius and the angle theta right there. So let me point out a few cases right here. So as far as polar equation, just like that, we can have r squared equals cosine of theta. That's one equation. It points out a relationship between the two variables, the angle variable and then the radius variable. Okay, we can have r times sine theta equals 1. It's an equation. It points out a relationship between the two variables. This is the angle variable. We take sine of the angle variable times the radius variable. That has to equal 1. It's a relationship. Okay. We can have an equation that is r squared equals theta squared. Okay. Or r squared equals theta. Okay, it's an equation pointing out a relationship between the two variables, r and the radius and theta the angle. Okay, so we can have so many polar equations out there. These are all polar equations. Okay, and so simply because, see, for polar coordinates we are primarily and only working with these two variables, and then so now at any time we're looking at an equation that relates these two variables and only these two variables involved. Those are the what we regarded as polar equations. Okay, and so now usually many textbooks deliver and allow me to just deliver the understanding that makes natural sense. And then once you see my explanation, you can always go back and read any of your standard textbook for what it formally means to be a polar equation. Okay, so allow me to just give that in a way of how we explain, so for what makes sense to be an equation. All right, so any of these is an equation. And so here's the thing. So in that way, it's a custom, it's a tradition that a lot of times when we're looking at an equation, we're gonna try to bring all variable terms. This is a variable term, this is a variable term, and we have variable terms and things all over. So the idea now is that we're going to bring all terms to one side. On any equation, we have our choice, and that choice became a tradition that we're going to bring all terms to one side. And so let's say algebraically looking at this equation, r squared equals cosine theta. I can subtract both sides by cosine theta and bringing my equation to r squared minus cosine theta equals 0. Okay? So I purposely display a 0 on the opposite side and all terms go to one side. So just like that here, we have two terms, two non-zero terms on both sides right here. So I have my choice to bring all terms, all non-zero terms to one side. And it's just me, I like leaving things, all non-zero terms on the left-hand side. So I'm going to subtract 1 from both sides here. So this equation here, I'm going to leave for myself r times sine theta minus 1 equals 0. Okay, and then with this one here, r squared equals theta, I have my choice to bring all terms to one side. So here I can do r squared minus theta equals 0. So what have I been doing here? The point now is that once we can bring all terms, all non-zero terms to one side and leaving a 0 on the opposite side right here, then we can see that the non-zero terms side is, we can recognize that, hey, it's simply a function, some function, capital F. Now, so some function capital F of in terms of radius and theta. See, this is some function, and we don't be worried about it's a function of two variables. It's not. We're not gonna learn what a function of two variables is. That's gonna have to wait until like your last course in calculus. We're only at the Calc 2, right? I mean, we're only at just some calculus course or some course past the trigonometry. But what I see here is it's just a function. It's a function of two variables, r and theta. So the same way here, this is another function of some other function of r and theta. And this left-hand side here, again, is a function of r and theta. So generally speaking, this is the reason I'm pointing this out is that throughout many textbooks, many standard textbooks in calculus, okay, a lot of times polar equation can generally be represented. Okay, so as a general or generally, any polar equation is in the form of a some function of two variable r and theta equals 0. That's a more general form of any polar equation. And then, of course, there are other precise details that I left out here in my own verbal explanation in this video lecture, but you can always find them in any standard calculus textbooks here. Because I just want to approach the understanding of polar equation in a sense of what makes sense. And of course, so it's just, if any of your points, right, has had at least one existing, remember, because polar coordinates, we have multiple ways to represent. So if any point of our if any of our polar coordinates points has an existing representation that satisfies this equation, okay, then we say that the polar point is on that equation like that. But so generally, throughout many textbooks in calculus, many standard textbooks in calculus, you're going to see that the textbook author deliver a general form of a polar equation as such, in that way like that. Okay, so that's the most general case of any polar equation. But then the easier version, easier to work with. So from that general case right there, usually we focus more on the form. So this is just a general case, and then there's a more specific case right here where, now let me write this down right here. R equals cosine of theta. See, one single variable r, linear term, on one side equals an expression completely in terms of theta on the other side. Okay, so that's one form. It's an equation, but instead of writing that as an equation, as one function in terms of one general equation form like this, I'm going to write this here. My intention here is to write this as to treat r as a function of theta. Okay. And so another one we can possibly find is that r can equals theta. See, linear term for r, and the expression on the opposite side is in terms of, see, this is a function of theta. So it's another form of an equation, of a polar equation, but it's specifically written as a function treating r as a function of theta. Okay, so you can also have r equals cosine, or how about sine of 2 theta. Okay, and so the one side is an expression in terms of theta only, and the other side is a linear term only, and one single term. Coefficient 1, linear power, right? And r equals. So this is again in that form of r equals a function of theta. Okay. And so these are the ones that we usually and most of the time work with in terms of polar equations. All right. And then we can also have r equals 3 plus, right, and 5 cosine theta. Okay. And there are many other equations, polar equations that written as a function in terms of theta right here. So we're treating r as a function. Okay. And theta is and on the opposite side is a function of theta. Okay. But so that general equation will have a graph, and any of these polar equations where we have already expressed r as a function dependent on theta variable right here, also will have a graph. Okay, we have a graph, and so the graph on any equations. The idea now is that so these are polar equations. Okay, so your textbook might use another form right here. So another specific form, not as general as this form I wrote down earlier, but see, throughout these quick examples I pointed out, we can also write a polar equation in a form where r is expressed in terms as a function in terms of theta, the other variable. All right, and so now back to what I was in the middle of saying just earlier. Then in either way, anytime we come up with an equation, either this form or that form, polar equation or rectangular Cartesian equation, we are going to have, there will always be a graph for that equation. So this is any polar equation will have a graph. We come to a graph. And so the graph on any polar equation is being regarded as a polar curve. Okay, the graph for any polar equation is regarded as a polar curve. Okay, so now in that way right here, let's get started into some examples. And so now I have to be clear a little bit. For now, any one of us learning through this video lesson is allow me to consider you as a beginner. Okay, and so for beginners who are in your first steps into learning how to graph and how to look at polar equations, then most of the time you are going to be working with those polar equations where it has been expressed as a function, as expressing r as a function in terms of theta. This is the one that we will be working with mostly. Okay, even most of the technologies out there, most of the graphing technologies out there can only handle the case of polar equations where your equation has already been expressed as r as a function in terms of theta. Okay, because it's a lot more challenging to express. I mean, to graph this polar equation where it's purely a polar equation, where it's in a more general form like this. Okay, and believe in my own experience, I've seen enough that most of the technologies out there can only handle the case where your equation has been expressed in the form of a r as a function, and then it's a function of theta. Okay, so that's why in my teaching here, I would like to specifically focus on the case where any of our equation is given as a function r as a function in terms of theta. Okay, so we will focus on this. All right, so now we are ready for, now sadly I didn't talk much about what polar equation and polar curve is, but now you are ready for getting into doing a graphing, an actual example in graphing right here. Okay, because now if the reason is, in my philosophy of teaching up to this point, I believe any one of you have seen enough how to operate with functions. And so that's why I can skip out all of those details, but I'm going to just get straight into how within what we already understood and how we added on top of that the idea of polar coordinates on top of that. Okay, but how we operate as a function it's going to be the same way, and any function has a graph. So now let's get into example 4 here, where we will be formally graphing a polar equation. Okay, so we're going to graph the function r equals, how about let's call this part A. Okay, let's graph the function, the polar equation r equals cosine theta. This was one among those quick little examples I brought up earlier. So this polar equation is specifically in the form where it has already been expressed as r being a function, and on the opposite side is a function of theta. So r is a function cosine of theta. Okay, and so now from trigonometry, anytime we are graphing, if we were graphing the function y equals cosine of x, for example, then we're going to be doing this. Okay, our graph is this. Right, and I'm not intending to revealing your trigonometry understanding, but cosine function in one period is like that. Okay, but ladies and gentlemen, this is not the graph we are expecting, because this graph right here, where each x and y, we measure x and y is in terms of x and y here is in terms of rectangular coordinates. So this is not the point of the graph. This is not the kind of graph we're expecting, even though it's true. I mean, a variable's name is just a variable name. A variable's name is just a variable name. So if you're seeing these as, if you're seeing these as rectangular coordinates, then yes, the graph is going to look like this, and end of story. There's no need to learn anymore. But what we want to learn here is that how do I see these as in terms of radius? This is radius, and this is cosine. I mean, this is angle. This is radius, and this is angle. And so in that way, this graph is not the one applicable for our case here. So here's how we graph. So any time that we think about this, every little background you have had in algebra comes back here. Okay? Anytime you are investigating a new kind of graph, or the graph for the new kinds of equation, we have to roll back and construct table values. Okay? And when we have a good hang of that, then we're going to start developing techniques and all that. And even we're going to start using technology, okay, to get the graph successfully sketched. Okay, but now the best place to start is to roll back to getting your table value constructed. Okay, and so in this equation given right here, how I see that now is that, see, and as I said earlier, R is a function, and it's a function in terms of theta. So in this equation here, I can see the role of the two variables is that theta is the independent variable, and R is the dependent variable. Let's make a note of that. Okay, this is the independence. That means we can assign any value for that. Okay, it's the independent variable, and this is the dependent variable. They are changing in their value. That's why they are variables. But then one of them is the independent one, meaning we can pick whatever value we assign for that. But then this one here has to come out being according to this rule. Take cosine of your independent value right there. Okay, and so now in that way, once we clearly identify our dependent and our independent value, then now we're going to bring that into a table of values. And then starting at this point, I'm going to switch back and forth between the decimals and on the board here, so that I can, assign. I'm going to do about a few entries on as a handwritten version here on the board, and then I'm going to switch over to decimals, because surprisingly decimals is powerful enough for me to build and do the work just like how I'm doing this here, and we can instantly see the points popping out. Okay, and so now in this way right here, let's construct a table of values. Okay, and as I said earlier, this is the independent variable, so we're going to pick one column for that, and this is the column for the independent variable, theta. And then this is the column for R, which is namely cosine of theta. Okay, so the value of theta, the value of R has to be calculated according to this formula. So whatever we give to theta, we calculate R by taking cosine of the given or specific theta like that. Okay, and it's a cosine function, so it's easy to, at this point, once anyone has learned past trigonometry, then you would think very naturally about those common values, common angles, theta, from the unit circle. Let's stay with it. Let's stay with that. Okay? So on the unit circle, we can start out with theta equals 0, the 0 angle. And so cosine of 0, okay, that gives me cosine of 0, so that gives me, this is going to be 1. Okay, this is the actual calculation. So our radius will equal 1. Okay, our radius will equal 1 when angle theta is 0. Okay, so, but remember, this is not going to be like this. It's not like 0, 1. Nope, that way was rectangular coordinates. Now we're looking at this as a pair of polar coordinates. Radius is here, angle is here, so this is really 1, 0. We gave a value. So the independent variable is on the left column, and the dependent variable is here. But then when we're listing it out, it's radius, angle. Okay, recall that from our earlier part of the lecture, where it's got you through and fluent with that skills of how to operate with the representation in polar coordinates. So really, it means when you are at 0 angle, so 0 angle in here, and 1 is somewhere out here. You are actually here. Okay, 1, 0. Okay, radius 1, but 0 angle. All right, so now I didn't get too far yet, not that far at all, okay, on my table of values, but let's quickly swing over to decimals to see what's going on. All right, to quickly see the plotting point right here. So now, here's all my decimals, okay, and I have already had the table constructed. So, just like how I have explained earlier in the earlier part of the lecture, that when a limitation with Desmos is that Desmos won't recognize theta, because Desmos purposely reserve theta when we actually just Desmos basically reserve theta for other purpose, and the same with R over here. So we cannot use theta and R here. But so on Desmos, here's how I constructed this table over here. So the t variable is a different name for theta. Okay, and so on this column right here, those are the values for the dependent variable, which is cosine of theta. Okay, so this is theta, this is R. So now I put in 0 for the angle theta, and I have 1. So just like that. So now in polar coordinates, that's why we had a point right here at the angle 0. At the angle 0, right on this line right here, I have a radius coming out being 1. That's how it is. All right, so now, so it's not 0, 1. It's not 0, 1 being in the usual sense as in the rectangular coordinates. All right, so now we are ready for heading out to the next value. So think as closely as the things as closely as possible to the unit circle. Okay, so the next common point on a unit circle is a pi over 6. Okay, so pi over 6. If anyone is anyone watching this video is still having fresh memory from trigonometry, then R here has to be, and now once you start getting a hang of that, then eventually I'm going to skip all of this. But right now the radius will be calculated. So radius is how far it's made from the pole, but radius in our thing that we're working here, in this kind of situation we're working, radius is regarded as a function of theta, of independent theta. So we choose theta independently, but radius comes out accordingly. Okay, so cosine theta, radius here is cosine of pi over 6. But cosine of pi over 6 equals square root of 3 over 2. Okay, square root of 3 over 2. So this is our radius in polar coordinates. So you have to start thinking polar coordinates. Polar coordinate. This is radius. This is angle. Okay. So don't try to look for where is pi over 6 on this axis. This is not your x-axis. I mean, this is still the x-axis, but that's not what pi over 6 is. Pi over 6 is an opening up. So as far as the opening up, it's about an angle like that. Okay. Pi over 6 about 30 degrees, and then we want a radius being a distance being square root 3 over 2. So square root 3 over 2 has to be a little bit shorter than 1, because this is angle 0 and then the radius 1. So angle 30 degrees angle. Okay, opening up in a positive direction. And then we are at square root 3 over 2, so somewhere slightly shorter. So we have another point right here. So this point right here is our square root 3 over 2 comma pi over 6. That's how I'm writing that point in polar coordinates representation. And I'm quickly going to run out of board space here. But now let's swing over to Desmos to see how Desmos is giving us that precise picture right there. All right, so with Desmos, okay, so now I'm going to skip one line right here for a reason. And I'm going to go pi over 6. All right, now the only downside with Desmos is that Desmos is not able to give me the value here in root expression. So that's all we can have right here. So this 0.86, I mean 0.866 of 254 here, and a lot longer is this is the value, the numerical, the decimal value for square root 3 over 2. Okay, and so let's now look at the graph in polar coordinates. See, when we are at angle pi over 6, see, and it's a positive angle, so angle pi over 6, then on that terminal side of the angle, okay, then we're looking at the radius being a square root 3 over 2, which is right here. So that radius is already shorter than this radius 1 when we are at that first entry on our table. All right. And then if anyone still wonder why I'm leaving this empty, I will come back to that and explain a little more about that. Okay, but now in that way, let's look at the next one in our table right here. So in our table, well, and again, like it's easy enough and very understandable that we're gonna just keep thinking as closely as possible to the common angle, right, in the unit circle. So after pi over 6 in a positive rotation, then here we're looking at pi over 4. So when theta equals pi over 4 independently, then we're looking at, so now you have seen twice or a couple times already. So I'm going to skip the actual calculation here. I'm just going to go r equals, actually I can still write a little bit of the calculation here. Cosine of pi over 4, that's r. Not as fancy as the earlier version, like r equals. So here just cosine of pi over 4. That is a positive square root 2 over 2. So this is radius, and this is angle. So now as that angle, it's a 45 degrees angle. Okay, and it's going to even be shorter. So square root 2 over 2 right there. It has to be even shorter than the 1. So now at this point, I'm starting to get, I'm really going to lose my scale badly here. So let's completely depend on our technology right there. We just know the calculation here, but we're going to leave that for the computer, for Desmos, to give the precise graph. Okay, so now on my Desmos here, the next entry down, yes, just that, I'm going to go with pi over 4. Okay, and this value, yes, ladies and gentlemen, this is positive square root of 2 over 2. And so look at the next point, it popped out here. So this is square root of 2 over 2 comma pi over 4 here. It's represented in polar coordinates. So we already start seeing a path that's going kind of bent, but going this way over here. And so it makes sense with the rotation being a counterclockwise rotation. So think about it. As we rotate the angle, right? So length can change long or short depending on the function. But that's how we come up with the graph. The fascinating part is that at the end, when we're looking back at the trace of all those points, we form into some kind of curve. And that curve is called the polar curve. It's a graph that came out, that generated by doing this polar equation. Okay, and we graph things by seeing theta as the angle and radius as how far it is from the origin, from the pole. All right, so now on my board right here, before I throw in the next point, you can see that we start seeing a rotating pattern, but in the end, we're still not so clear about, because right now it seems bent, but we only have 3 points so far, and there's such a large gap between these, because now from pi over 6 to pi over 4, the jump is only a small jump. Okay, but it looks like in a way throughout all the common angles we knew, then it looks like we skipped this one right here. Okay, so think about it. This is right here at that angle on the graph. It's a pi over 6. Okay, and this is a pi over, it should be a pi over 12, because it looks like exactly half angle between the 0 angle and the pi over 6. So this has to be a pi over 12. Okay, and so and it makes sense that if we're adding a pi over 12 to pi over 6, we're ending up with a we're ending up with a pi over 4. Okay, we can quickly do the math like that. And so the point I'm trying to make now is that I'm not completely happy with the refinement, with the fine level, with the fineness level of these the partition points, with these points that I'm choosing right here, because it leaves it leaves a gaps on my picture right there. Okay, and actually let me bring up one more point right here. 2 more points, and then I will get back to what I meant earlier, and you will understand that a little better. So the next point on the unit circle, the common point on the unit circle is a pi over 3. And so radius can be calculated as cosine of pi over 3. Okay, and this will give us, according to the calculation here from the unit circle, then this is going to be a 1/2. All right, and so quickly on Desmos right here, okay, I can put a pi over 3, okay, and for anyone to know, just simply type lowercase pi, it will pop out, it will automatically pop out that pi symbol right here. But see, with the new point, when angle is at pi over 3, positive pi over 3, we're looking at radius 0.5. So it's this new point just now popped in right there. Okay, see, before we complete that point, right, we didn't have that. Before we completed that expression for the theta angle right there, then we didn't have that point. And then now when it's completed. Now that is the angle pi over 3. Okay, and so now the next one I'm doing here is and it allowed me to leave a little bit of an empty line right here, but the next one I'm doing here is a pi over 2. It's a 90-degree angle. Okay, and so right there, okay, so it's a little hard to see, but we actually, there's that green point that just now popped out right here once I completed that pair. So radius is actually 0 on pi over 2 angle right there. Okay, well, let's find out. Back on the table, I'm already running short of space here, but with my table over here, theta, and then this is r equals cosine theta. Okay, I'm continuing with that table. Then when theta is pi over 2, we're looking at cosine of pi over 2. Okay, which is a 0. That agrees with whatever decimals was given. Okay, so now I'm ready to bring back what I was about halfway of saying earlier. Now, if you're looking at the graph right here, if we're just simply staying with the common, okay, let me zoom it in a little more right here. If we're just simply staying with the common points, and we have too much of a big jump right here, and then also another big jump here, even though we start seeing that things are forming into like a bent path right here, but it's not successful enough to see the complete change, to see how things are changing and see a smooth graph like that. So now I'm gonna, and notice in these 3 points, the angle changes just about a pi over 12 angle. Because think of it, the amount of angle here, and Desmo is doing a really good job with the grids right here, with the polar grids, where each sector right here is perfectly 1/24th of the entire circle right there. So there are 24, see, 1, 2, 3, 4, 5, and 6. 4 quadrant, each quadrant has 6 little sectors like that, equally spaced section. So that means that the complete rotation right here has to have 24 of those little sectors like that. So in that way right here, it has to be a pi over 12 in each of these. Okay, so now I'm gonna refine my table. So I don't want to, and for us here on the board with the table values, traditionally with the handwritten version, it's hard to calculate pi over 2. But now with the computers, with decimals, it's a lot easier. Okay, so now let me show you. So now my plan now is I'm going to fit in that angle pi over 12 here. So it's a 1 pi over 12, 2 pi over 12 now will become pi over 6, 3 pi over 12. See, 3 sectors open up, right? 3 sectors of a pi over 12 angle. So 0, pi over 12, 2 pi over 12, 3 pi over 12s, 4 pi over 12s, which is a pi over 3 right here. And by the way, 3 pi over 12s was a pi over 4. That was the value right here. So we've seen all that. Okay? And then now there's supposedly this is 5 pi over 12 right here that we didn't get to. And then this pi over 2 is the same as a 6 pi over 12. Okay? So now let's throw in these angle values and half decimals calculated for us. And that's what I did here by leaving that those empty ones like that. Okay, so now just 1 pi over 12 allow me to write it that naively a little bit, that naive way a little bit, but 1 pi over 12. So just now there's that point popped out right there. All right, so now we start being more convinced that it's forming into a circular path, but the circular path doesn't go around the center of our circle like this. It's kind of path and it's bent down right here. Okay, so that's why it's even more beneficial if we put in another, trying to find out what that point here when the angle is at 5 pi over 12. Okay, so pi over 2 is a 6 pi over 12. So I'm going to put in the 5 pi, okay, over 12. All right, and so now these are the values. Okay, and then just now the decimals just popped out that point for us here. So now it's even more clear that it's already formed into a semicircle. Okay, right on that path, and the angle goes like this. Okay, opening up, and then as the angle opens up, right, the length gets shorter. See, the length keeps getting shorter, and now when it's pi over 2, then the length shrink down to 0. Okay, so just a quick the clarification, but on papers and pencil, you can still indeed calculate these value, the value at pi over 12 Okay, the value at pi over 12 and the value at 5 pi over 12 here. You can still calculate that. Okay, because here's how I'm seeing it. It's just a little bit of a trigonometry review right there. Hopefully it's beneficial for anyone learning from this lesson in case your technology is not immediately available with you. Okay, and so if we notice that, so everything we're doing right now is we want to verify how decimals got those decimal point on the column for the R right there. Okay, so basically we need to know how to calculate cosine of pi over 12. But cosine of pi over 12 is the same as cosine of pi over 6 angle, which is the common angle, and divided by 2. Cosine of pi over 12 is the same as cosine of pi over 6 over 2. And pi over 6 is recognized, has always been recognized as a common angle in your on your unit circle. And so in that way, now we can, let me remind anyone viewing this lesson, you can use the half angle formula. Okay, and so with the half angle formula, all right, and since pi over 12 is in the first quadrant, so we're going to use the following half angle formula. It's going to be positive, because recall that the cosine of a half angle as a formula, it's going to be plus and minus square root of 1 plus cosine theta over 2. Okay, so this is the half angle formula for cosine. So cosine of half angle is there are two formulas, two versions, plus or minus. So we will choose a plus here simply because our angle, our pi over 2, our theta over 2 angle is in the first quadrant. So we just have to know whatever quadrant that is, so to decide to use the proper formula over here. And so now in that way, I'm going to need space, so I'll erase this. And this is going to be positive square root of 1 plus the cosine of pi over 6. Okay, so we recognize that pi over 12 is the half of pi over 6. So now that's the formula to use. And we divide by 2. All right, and so this is the reason, and this is how, see, so it's 1 inside that root. We have 1 plus cosine of pi over 6 is a square root 3 over 2. And then divide all that by 2. And that's the value. And if this is a formal trigonometry course, I would spend my time explaining for my students how we're going to reduce this algebraically with the roots, and it's going to come out a lot nicer. But in the end, so we already had decimals, so that's how decimals got that value being quite lengthy decimals right here. But see, pi over 12 is a 0.9659 and a lot longer. Okay, and that's what it is. And so now just want you to know that there is still a way, even though we use angles that are not too common from the unit circle, but there's still a way. So just the same with that, if you want to verify, you can use 5 pi. You can still calculate this cosine of 5 pi over 12 by using the half angle formula. Okay, so again, I'm seeing so I'm seeing cosine of 5 pi over 12 as cosine of 5 pi over 6. This is a common angle, okay, but over 2. So I'm seeing 5 pi over 12 as half of 5 pi over 6. And this is common angle. So again, it's going to be, but 5 pi over 12 itself right here is still in the first quadrant. So I'm going to have to use a positive roots formula. And here I'm going to go 1, okay, plus cosine of the 5 pi over 6. Okay, and I'm dividing that by 2. Okay, 5 pi over 6, cosine of 5 pi over 6. So in this case, it's a big square root. Inside of that numerator, I have 1 minus root 3 over 2. And the other one, and then in the denominator, over 2. Right there. And this is the reason how decimals came up with this value for us right here. All right, so any of these has a way to find out right there. All right, but so in that way, now you can see that so in my way of moving it, what I've been trying to point out is now past this pi over 2 angles here. I'm going to start to move. I'm going to start moving my angles. I'm going to start moving my angles in units of pi over 12 like that. So that means the next angle I'm putting in, right, in my table of value, in our table of values, is going to be, and now I'm gonna completely stay with decimals right here. So the next one here is gonna be a 7 pi over 12. Okay, and then it gives me this value. But see now, in case anyone didn't notice, okay, before we completed that, okay, these are all the points. Now allow me to put in the point 12 and observe this graphing area right here to see where the new point jumped in. All right, the new point jumped in right down here. But wait a minute, 7 pi over 12 is supposedly this angle right here. So shouldn't we be expecting some radius on this? But think about it, the value here is negative. See, decimals calculated that for us. So at that angle, we actually ended up with a negative angle. I mean a negative radius. That makes sense why, according to our way of knowing about polar coordinates, then at any angle, right, negative radius is going to be the opposite side of that. That's why decimals put that point here. And now anyone is ready to completely follow along with me, so for me to finish all the way to the end of my table right here. And it's going to be a lot faster compared to the table that we have to do with the hand sketch version right here. Okay, and so now back on my decimals, the next point I'm going to have is going to be an 8 pi. Okay, 8 pi over 12. All right, so now 8 pi over 12, here's that next point that came out right here. It's still a negative value, right? And 8 pi over 12 is this point right here. I mean this angle right here. Right here. All right, it's the same as a 3 pi over 4. Actually, I mistake. It should be the same as a 2 pi over 3. All right, it's the same as a 2 pi over 3, and so it's a negative radius, so we came up to this point right here. All right, and then the next one here is 9 pi over 12. Okay, and this is really the same as the 3 pi over 4 right here. And so the angle is here, but we had a negative radius, so it pops out this point right here for us. All right, and so now the next one I have. So and now as we observe the pattern, it looks like, and then here's the orientation of those points. These are the changing in the points right here. So it's going in that path right here, and it still seems to form a nice circular path. Okay, it still seems to be forming into a circle path, like a circular path. So the next one here on my table is how about a 10 pi, okay, over 12, and 10 pi over 12 is essentially the same as 11 pi over 6 right there. Okay, and 10 pi over 12 is the same as 5 pi over 6. So the angle is here, but then since we're having a negative angle, a negative radius, it's gonna be that point down here. And then the next one, 11 pi over 12. Okay, 11 pi over 12 is this angle, but then having a negative radius, that's how we came up with that point right there. And then the next one down on my table here is a 12 pi over 12, which is ridiculously a pi, but allow me to show these fractions of pi over 12 right there to show you that we can jump in small steps, and each time we jump by one additional step right there. Okay, and so now that new point is supposedly here. All right, it's coincide with that point right at 0, 1. So now it's 12 pi over 12. The angle is here, but the radius is -1, and that's why it falls back and comes and becomes the same point with 0, 1, like that for that. All right, and so now think about the impact right here. Further, as we continue with our table, the next one would be a 13 pi over 12. Okay, and we don't see any change, but this is simply because, see now when we're at 13 pi over 12, which is down here, okay, 13 pi over 12, then our angle, our radius is negative radius, okay, and so that's why we have this point. So it looks like we complete this circle here, and then we're starting to loop around with that circle, okay, and then in the next one here, 14 pi over 12, okay, and we're at the negative radius. 14 pi over 12 is about down here, 7 pi over 6, the same as 7 pi over 6, but since the radius is negative, we're ending up with that point here. So now definitely it's clear that we're looping around this circle over here. All right, and so now I'm going to complete all the way to the end right here. So 15 pi over 12, okay, and then 15 pi over is all of these, this one right here. All right, that one right there, 3 pi over 4 right there. I mean 5 pi over 4 is down here. Okay, and then that's the radius being negative. It's a negative radius, but the angle is down here, so that's why it popped back to that point. So now we're even more and more firm that we're looping around with that circle that's already completed at 12 pi over 12. It was already completed, that circle, and then we loop around one more time. And so now in my next value, I'm looking at 16 pi over 12. All right. And 16 pi over 12 is the same as 4 pi over 3. And now I'm looking at negative 0.5. So negative 0.5 is this point right here. All right. And then the next one is a 17 pi over 12. Okay. And 17 pi over 12 is down here. Okay. And I'm looking at that value. All right. Being a negative radius. And then my next one is 18 pi over 12. Okay, and it's a 0 radius. So 18 pi over 12 is this angle down here, 3 pi over 2. Okay, and the radius is a 0. So we swing back to that 0. All right, and so it looks like we have gone through one complete cycle of that, and we already finished another half loop of that circle right there. So now let's do it further jump. So now it's going to be 19 pi over 12 right there. And so 19 pi over 12 is this angle down here, but it is this positive, so the angle is here and it's a positive angle, so it's right here at that point. Okay, and now I'm going to look at 20 pi over 12. Okay, so this is 20 pi over 12 right here, and then that's the same as 5 pi over 3, but then the radius now is calculated as a positive quantity, and so now we can look at that one right here. And so now I'm even more firm that we will be eventually completing that curve like that. All right, so now let me just pick up the pace here. So 21 pi over 12 is this angle over here with that point as the radius. So the radius here is whatever it reached right there, 0.707, so on and so on. 22 pi over 12 is this point right here, which is the same as 11 pi over 6. And then another point that we have here is 23 pi over 12. Okay, another positive value. So 23 pi over 12 is this guy, is this angle over here from the positive direction. Okay, and then we're looking at the positive radius. And then the last one here is a 24 pi over 12. We're looking at a positive one, so we complete that circle. So as we were attempting to build our table of values using the complete circle, the complete to make one complete rotation for theta right here, and one complete angle rotation for theta, then this graph right here generate a circle like this. Okay, center at 0.5 comma 0 right here in rectangular coordinates. Okay, and then it's going to traverse, it's going to travel around that circle for 2 loops right here. Okay, and so now let me bring up this interactive picture right here for you to even have a better understanding. Okay, so I'm going to switch over to a different version of my polar sketch right here. Okay, and so here's the thing. I designed this activity, I designed this little demonstration so that you can see. So now the angle 0 is right here, and this is still for the same function, cosine theta. Okay, but now I'm gonna open up. So now I want to see the actual trace. So now I'm gonna, all right, so now I'm moving up. You see this is my handle right here, and then the solid line is the actual rotation of the angle, and then this dotted line on the opposite end is there in case our points will jump and become a negative radius. So it's going to be the opposite part. That's why I put it dotted here. But right now we're at about that angle pi over 12 like that, pi over 12, and that's why it's right there. Okay, and it's giving me, so it started out with radius 1, okay, and it's showing radius, and it reached to that. And then now I'm going to move up to, all right, that's 2 pi over 12 like that, okay, which is a pi over 6. And see the red point is moving on the handle over here, so the angle will keep opening up. And that's what I'm seeing, okay, that's what I'm seeing. And then the radius keeps shrinking. See, the radius keeps shrinking, but the radius are still all positive radius right there. Okay, but now it's forming into a path. So just like that, when we were recognizing with our, and allow me to zoom this in a little more, but when we were looking at our dotted graph, the graph with the actual plotting points, then it did form into that shape right here. We see, as angle were opening up, these are the lines for our grid right here. And as angle were opening up, we were losing lengths. Right, we were losing the radius. All right, and so now let's see more into this interactive demonstration right here. And so now I'm going to move this to, all right, so just right about there. I'm going to even open up to 3 pi over 12 like that. Okay, and then as I move, my curve is a lot finer. So those points we have seen earlier are all on this path, and now we can even see the better version that indicates the direction of this rotation. Okay. And now I'm going to move to the next one right here, to the next angle right there. All right, there we go. Okay, and then now I'm going to move to 5 pi over 12 right here. All right. All right, so 5 pi over 12 is right there. And then now I'm going to move to the next one here. That's going to be 6 pi over 12, which is a pi over 2. All right, and so now once you have a good hang of that, now let me complete so half rotation. And so now we're going to start seeing some, see, when the angles open up more than 90 degrees or more than pi over 2, then we start, now according to the dotted shape here, according to the dotted graph, the dotted plot, and anytime that we were out here, right, then we started having negative radius. And so that was what's happening here in our picture. Here, see, negative radius. That's why the actual graph appears on this opposite end right here instead of the actual positive angle. Okay, and then here's a half of our, so this solid line right here is to represent the actual opening up of the angle. It's coming close to halfway. Okay, half rotation, half complete rotation. And look at the graph. We already complete one graph like that. Okay, and now as I keep going, then that point right here keep changing, keep looping around that same green circle, okay, until we make one more loop right here, and that's about where we stop. All right, and so now this is, ladies and gentlemen, this is actually the graph of our function. The graph for our polar curve R equals a cosine of theta. Okay, so that's how it has been done, and I try to, it took a lot of time and explanations, but that's how we're doing it. Okay, so the reason, all right, so now allow me to explain a little bit about the reason why we have to stay away from using theta and actual R on Desmos here. So you see, Desmos is also powerful enough that you can just simply type in R equals. Now I'm using lowercase r and cosine theta. Okay, look at what it did for us right here. Boom, it gave us the graph. But this is not good for learning. I have to emphasize that. If we just, and this is the same way as how many graphing technologies out there, including our TI-8384 calculators and many HP graphing calculators. If we just simply typing in the equation into the graphing technology, it just gives us the graph. But without, we lose all that understanding. We will lose all that understanding about where the graph is going. Okay, so as far as learning, just simply typing it in. And that's what Desmos reserved. For Desmos reserved the letter R, the lowercase letter r, and the actual theta for any time users want to enter, just quickly get the graph, the polar curve that instantly came out. Okay, but now as far as the learning, I want to show my students, I want to show my viewers the actual change in the angle, to how it generates the graphs along, as well as how you see, that all of that the positive and negative radius. And that's the reason why, when I was creating these activity and throughout some of my explanations with the use of Desmos, I have to highlight, if anyone plan to use Desmos for polar curve and use that to make some good learning for yourself. Then use the letter T for theta. Don't use theta, but use T for decimals, for angle theta, and then use just anything else outside of lowercase letter R for your function. Okay? And so now we are ready for another polar curve. So let's look at part B of our graph. And now for this one right here, we can start speeding up the process a little bit. So now I'm going to, in this example for part B, let's graph the polar curve R equals 3. Okay, R equals 3. R equals 3. So here's our, so keep in mind again, we see this polar curve as expressed as R as a function, expressing R as a function in terms of theta. Okay, so theta is the independent, but we actually don't see theta in this equation. It's actually already a constant. It's actually already a constant. So now I am going to turn over to decimals. All right, so now to begin, now when we are at theta equals 0, 0 angle, we have a point out here. And then when theta equals, and again, just like part A of the example, I'm going to decide to go in a jump of angle about a pi over 12 units. So here it's going to be 1 pi over 12. We have a point right here. Okay, and I'm going to jump again. In my table of values, see, this is the column for R and this is the column for T right here. And then for my 2 pi, okay, over 12, okay. 2 pi over 12, I have a positive radius equal 3. Just like that, specified already in the table here. And then when I'm getting to 3 pi over 12, it's the same. See, that's why the decimals is even trying to be a little too smart right here by just constantly put all the output values here, even though without having any inputs specified, because it already knew. Okay, and here at angle 3 pi over 12, which is the same as a pi over 4, we still have radius 3. So it looks so far it's forming into a circular path center at the pole right here. All right, and so now this is a 4 pi over 12 is right there. See, there's another point. And then now I'm looking at 5 pi over 12, and that's another point that popped out right here. And then 6 pi, okay, over 12. There's that point right there. So all of these points so far stays right on that circle at radius 3. Okay, and doesn't matter what angle we're at. Okay, so we're independent with angle. We're always at radius 3, no matter where we rotate. And so now it's going to be the next one, 7 pi over 12. It's even more confirmed that even at further angle, we're still at radius 3, positive 3. Okay, and then now 8 pi over 12. Okay, and then here we have 9 pi over 12. Here we have 10 pi over 12. Okay, 11 pi over 12. Okay, so these points are all lining up right there. And then 12 pi over 12. Okay, and then we have 13 pi over 12. Okay, so we keep having more points popping out, but they're all on that nicer circular path center right at the pole right here. Okay, and then I'm going to move on to 14 pi over 12. Okay, and 15 pi over 12. Okay, 16 pi over 12. 17 pi over 12. Okay, 18 pi over 12. Okay, all of these points just keep popping out on us right there. And then now I'm looking at 19 pi, okay, over 12. All right, and so now that is apparently, that is clear enough. That is clear enough for us. All right, so that is now clear enough for us to see that all of these points are on a circular path right here. So in that way, now let me swing over to my other version right here, the version with the handle and with the fine graph right here. These are just scatter point. These are just points that lining up, and we already saw the path. But let's now really show the path right there. All right, so now I want to zoom out a little further to show radius 3. Okay, so radius 3 is here. All right, and here's my handle. All right, and so now I'm going to go rotating. All right, so as the angle opening up, we always going to maintain, no matter where the angle is rotated to, we always going to maintain that that radius 3, okay, throughout the entire rotation. And now when we reach one complete rotation and none of the radius hits to the negative side, okay, so we are going to have that, okay, it was all here. All right, so that complete our graph right there. Okay, so this is the graph for our polar curve r equals 3 right there. So kind of like as a rule of thumb, we can start drawing out anytime we have r equals a constant value, it's going to be a nice round circle center at the origin right there. All right, so we have seen two problems in graphing, and you have seen that through the demonstrations of that. Okay. All right, so now for anyone studying about polar equations with me and polar coordinates with me, I decide to allow you and I decide to incorporate the understanding of how to operate with Desmos. Instead of the standard TI-83 or 84 or any of the graphing technologies on the market out there, I decide to teach you how to use Desmos, because you can already see throughout my explanations right here that Desmos does a good job, does a very well done job in terms of it's good for your learning. Especially you have seen how I was putting up the plot points earlier, and it forms you a path, and you can see the path, how the path changes depending on where you put your angle. Okay, so now I'm going to also quickly, I'm going to spend a little time show you how to construct your own table of values, how you can use Desmos to construct your own table of values so that you can help yourself when you are encountering with some more challenging polar curves like that. Because in all of the reason I'm doing this is that throughout, eventually anyone learning about calculus, anyone learning about polar equations, you have to use a technology to get your curve. But a lot of time, or most of the times, I see the kind of technologies being sold out there on the markets only just, once you're done typing in, it just gives you the equation, but without much understanding. So with Desmos here, once you construct your table, and then you should be able to see how your point changes going around the graph like that. You can see how the graph is actually constructed from scratch with Desmos. And so I'm going to show you that vital skill so that, on your own time, when you face with problem that gives you more challenging polar equations to graph, then you have a way to get started. Okay? So let's swing over to and you can use any general web browsers. You go to desmos.com right here. Okay? So it's just that, desmos.com. And then your main page is going to look like that. You're going to just simply hit on graphing calculator. All right, and so now you have seen that a little bit earlier, but now I'm going to really emphasize that. But when you're in a graphing mode right here with Desmos, click on that little icon right here so that we will change the graph to, because right now by default any graph is in rectangular coordinates. But now we want to switch over to polar coordinates. We're going to click on that button right here, okay, and then we're going to click on that that says this is polar graph like that. All right, so now you're in polar mode, okay, and so now allow me to use that example for part A of example 4 we've done earlier to show you how you can construct a table of values. So that was how I did that before I gave the lecture. That's how I built that, okay. And so the equation we want to use here is r equals cosine of theta. Okay? But now keep in mind, again, if you're just typing in the exact r equals cosine theta into your Desmos just like that, r equals cosine theta, then we're not learning anything. Because once we're done typing it in, Desmos just simply throw the graph at you. And here you go, here's the graph. So we're not learning anything. We just see that. We don't see the change in how it affects the graph, how the graph gets more generated as we change the angle. So in that way, here's how we can actually do that. So I've been having that throughout this lecture. I've been having that the advice that anytime we're about to plot in polar coordinates with Desmos, stay away from the lowercase r and the theta variables right here. Use t for or anything else for theta, and then use any other one for r, but just don't use the letter r for radius and theta for angle. So I'm gonna, for start, it's just my style here. I'm gonna introduce the radius as a function. See, radius is a function of theta. So in our function here, r, capital R, is cosine of t. Okay, and Desmos will automatically pop out a graph. We can hide that graph away because this is not the graph that we need. This is the graph in rectangular coordinates, so we don't need that graph. Just hide it away. I only need to define this r so that we know that the radius is always a cosine of whatever angle theta. So it will be used for the later calculation. Okay, and now from that, I'm going to hit enter to enter into one new cell right here, one new command line entry. So now once I'm in a new empty command line entry, I'm going to click on add button right here, and I'm going to go down to table. Okay, I'm going to click on that purple button right here to clear that out. I don't need that. I'm going to clear that out because I only need to use this table as a table of values. And so now I'm going to change this column to t. Okay, all right, and then you might see some change here. Don't worry about that. That's just let's leave that part for Desmos to automatically do its own work right here. But this column right here is the dependent variable. But sadly, Desmos is not powerful enough for me to just type r here. So Desmos is not doing that. So Desmos is still going to require you to put the actual cosine of t. Type it in down here. So I'm going to type cosine of t. But see, so now this is r. This is radius as a function, as the dependent variable, and this is t. Okay, and then we can leave that there. I'm going to click into another empty cell right here, empty command line right here, and I'm going to type in. So Desmos is still limited in terms of putting the actual the polar coordinates points right here. So Desmos will not understand r comma theta. Okay, Desmos won't understand that. So in that case, I have to do the following. I have to give my point as x and y coordinates in rectangular coordinates. Okay, so in rectangular coordinates, see, we learned previously that prior to this point that x coordinates, okay, can always be radius times cosine theta. Okay, and then the y coordinates in case we need to plot any of these points. So so Desmos doesn't have the actual plotting points, point by points for the polar points. Then we're going to use the rectangular coordinates. But to make sure that those rectangular points coordinates falls right on the actual the point with the relative with the relative theta and radius right here, then we have to specify. So y here is r times sine of theta. This is fundamental, and that's why we had to learn that prior to getting to this graphing point right here. Okay, and so now here's how I'm doing that on Desmos right here. So the radius is this defined function. So I'll just go type radius, but then we need to multiply. It's just the way it is. X coordinate is always radius times cosine of t. Okay, so there we go. We have that. And then that's the x component. Now I'm going to comma. The y component is the radius times the sine of t. This is the bare bone of that. This is the structure, the bare bone of that. Okay, and so now that's all it is. Once we're done with that, then the function is ready. I mean, the graph here is ready to automate. Okay, so now if our function is a cosine of t, okay, so just like how I did, I'm going to go 0. Okay, that gives me radius 1 right here. It pops out. So Desmos is smart enough to calculate these values automatically for us. So 0 angle for theta, radius 1. And that's why we have that point right here. So once you've had that done, set up as one command right here, you can just leave it there the whole way. Okay. And now I'm going to click on that, okay, and hit enter. That's my table will automatically be extended. So like I said, I used the 1 pi over 12 jump right there for each angle change. So just like that, in my next angle here is going to be a 1 pi over 12. Okay, that's how I ended up with this next point right here. See, it's the angle is pi over 12. See, the angle is pi over 12, but now radius is that whatever it was right there being this much, but positive radius. Okay, and then now I'm going to jump to the next one. All right, and so 2 pi over 12. Okay, and just type that, and it popped out the next point right here for me. All right, and then now you can start seeing that as we change angle, we learn better that as we change angle, then we have more, and we can see how these points form into a path, and that helps the learning a lot better. You will have a much better understanding of your polar curves, of how it behaves as the angle theta changes. Otherwise, if we just let the calculator give out immediately, here you go, here's your polar graph, you will learn nothing. Okay, so I love showing my students and technology. Okay, but I want my student to use technology in the right way so that it gives the right result for us rather than just completely depend. I don't want my students to depend on technology. Okay, we use technology as a tool for us because we develop them to help us, but we don't want them to take over and become our masters, telling us what to do. Okay, and so now back to that. See, now I can just continue to, and doesn't matter how far, there's no limitation. I haven't seen any limitation in terms of how far the table can be. So the next one here, I can go 3 pi over 12, okay? And then, so now optionally, if anyone would like to change the color of these plotted points, you go to that entry right here. Now click and hold for a little bit. Click and hold. It will pop out a little menu right here for you to select. So now you can select a different color right here. So if you want green, like how I was doing that earlier in my in the example itself right here, then now all the points are changed to green right here. All right. So now one more thing to understand about this. So what if we didn't graph? What if we didn't graph this one? What if we graphed a different one? Okay, what if we graph? So that template I showed you with Desmos was already pretty much 90% of the work already. Okay, and 90% of the work on that template doesn't need to be changed. What if now you need to work with r equals 5? We use a different function. How about in the example part B of example 4 right there? I was using r equals 3. Basically, it was a different curve. Different functions of theta, or it was a different function of theta in part B of the example. Okay, then so on your Desmos, this is all you have to do. On your Desmos, we go here, okay, and change that to 3. All right, and then don't worry, all the points here disappear. And then now here, all right, here we're gonna change that to also 3. Okay, all right, so now I'm going to zoom out. I mean, you can click up and down here for zooming in or zooming out, or if your mouse has a scrolling wheel, you just scroll down and that zoom out, and you scroll up right there, and that's going to zoom in. Okay, so we're going to zoom in. That's how it happens. So 0 angle gives me this point, pi over 12 angle gives me this point, and so on and so on. So here we're looking at 4 pi over 12, that's this next point. 5 pi over 12 is that next point right there, and so on and so on. Okay, so you never have to change this. Okay, but when you change your different functions, you just have to change at that entry right here, type in your new function, and also type in it here, so that it will pop out the correct value for you to check for consistency right here. So those are the two things that you got to be watching out for. Okay, and so, but other than that, that's how you can create. That's how you can rely on Desmos to quickly get the graphs of any polar curves, right? Using plotting the points by plotting the points. So instead of doing that by hands, that old-fashioned method, it's still here, but we're doing that with Desmos, with the assistance of Desmos. Yeah, that's making it easier. Okay, and so that's how you did that. Now, in addition, I also want to show another Desmos tool that I developed it myself. I'm not gonna teach students how to develop this because it takes a lot of time. But I already developed that, and I will allow you to use this. Okay, but the real truth. All right, so this is the truth about that little activity that I've been doing using the whole time right here. Okay, so I will, if you are now this for this part right here of the lecture, I am specifically communicating with students who are learning math directly with me, learning about polar curves directly with me. Then I will send out to you, if you are a student registered in my class right here, I will send out the link to this specific Desmos activity right here. so that you can see the graphs, the actual fine-looking graphs, and you still maintain your understanding. So this is what I'm doing here. I mean, if you notice right here, let's go back to that function. Let's go back to that function that we did in the graphing, particularly. All right, so in example 4, part A, we did this. So this is our function, okay, of theta. This is our function of theta, okay? And so now I'm going to switch over to my Desmo screen. Like I said, I will give you the actual link to my students. I will give you the actual link that has this completed Desmos activity already. And then all you have to do now is that if you want to see the new functions, see, like I just now point out that quick example, we want cosine of theta. So here you can type the actual cosine theta, okay? And then don't click anything else, just type it in like that. So once you have the link given to you, this is the part, this is the entry that you can freely change depending on what function, what curves you want to plot, okay? And then your curve is there, okay? And so now, once you had that, you might want to leave this empty, but simply click on that circle, okay? It's gonna pop out the rotating handle. Okay, the rotating handle, it has a little red point right here in case anyone noticed, and there's a positive angle side and there's a negative ray of that. And now you're gonna click on the polar curve. Okay, so by clicking on that, it will start showing you the graph. So after you click on that, it will pop out a point right here. See, when I disable that, then it hid away that point. But now when I click on polar curve right here, okay, and then it has that point. So now I'm gonna use this, okay, to change. So as I'm increasing my n right here, see, then that's how I change my angle. All right, and as I increase my n, it's changed my angle. So now you can see that as I move along right here, as I move along, okay, and as I move along, then as my angle is opening up, then I'm changing this, okay, and that becomes the graph that looks just like the graph in our activity. Okay, and you can see this number is changing in the sense that, see, 90 here, I programmed this, I prepared this to go in the degrees convention. Okay, in the degrees convention, and it takes a little bit of math, not too simple, but I use the n here as a degrees. So 90 degrees is about a pi over 2 rotation right there. Okay, and now we're going to about 180, and you can see that some part of the radius is becoming negative, just like how you have seen that back in the activity. And this is the truth behind the scene of how I was doing that the whole time right there. Okay, and so now when I go more than 180, right, and then ready to complete one circle, right, and then it is 360 right here, we completed one circle. Now by default, I set it up to roll 2 rotations, so it's go all the way to 720. But that can also be changed. If you want to change that to only one cycle, then you just simply click. You see how the mouse cursor became like a little ready to type cursor right here. Click on that and set your up limits here to 360. Okay, and then click simply anywhere outside of that. So it's maxed out. It won't go anywhere beyond 360 for rotation. Okay, and then we turn on that. All right, and then so just like that. As we complete our full rotation on the angle is here, as we complete our full rotation on the angle, then the point on the graph here is looping through that graph twice, okay? And you can see from the first time when the graph is set up right here and to the beginning, okay? And then there are even other cases that, so there are even other cases where your function is even more complicated. So by default, I set this with that Desmos template right here. Pretty much by default, we always gonna change the angle from theta, anywhere theta from 0 to 2 pi. That's one complete rotation. Okay, but in case you need to change even more, because there are times that you need to go with an angle from minus 2 pi, okay, to 2 pi, 2 complete rotation to see the complete graph of your polar curve. There are curves like that, okay, to see a complete graph. Then in that case right here, if you want to go from minus 2 pi to 2 pi, right, from minus 2 pi and 2 pi, this is what you need to do right here. Okay, so on your decimals again, now you go to that little folder right here that's called interval. Click on that arrow, it's going to point out and it shows all the settings that I already programmed. And these are some of the settings you can also change. Okay, so you see right now, because I want to go from 0 to 2 pi, so I set that as the low end of the interval is 0. And then the upper end is a plus with pi over 100, I mean over 180 times n. This is how I indicate that as I move. And actually, this is wrong. I shouldn't change that. Okay, we can just only quickly change this. Okay, and no one, you don't need to touch that slider right here, but this is default at 0, and that's default at, and this is at a plus pi over 180 times n, and n came out from that value right here of the slider. Okay, so as we change that slider right here, then this is how we move. See, one rotation from 0 to 360 is the same as one rotation from 0 angle in radians, from 0 angle in radians to 2 pi in radians. That's how I programmed the calculator, okay, the decimals calculator. So now, if we have to use a rotation that goes all the way in radians from minus 2 pi to 2 pi, because radian is the more standard units when we start dealing with trigonometry. And so if we need to do so, then on your calculator, I mean on your decimals right here, you will change this value right here. Just type it in, don't worry about the slider, type it in minus 2 pi. Okay, and it will automatically recognize the bottom. But then, all right, so, but here's the thing. As a matter of fact, this is only, see, look at the end right here. 360 degrees is only one rotation. But the interval from minus 2 pi to 2 pi, it's actually two complete rotations. Two complete rotations, so keep that in mind right here. So, and believe me, for any students who already learned past trigonometry, your mind is more mature than your mind is more mature, so you are ready for me to give all of these explanations right here. So 360 in my decimal setup right here is only good for one. So once you complete up to 360, you only run from minus 2 pi to 0 here. But if you want to reach all the way to 2 pi, then you have to change your n here to 720. Okay, because from 0 degrees to 720, that's two rotations. So now with something like this, you are rotating 4 cycles like that. Okay, so that's one cycle. I mean, that's here. All right, so that's one cycle. And then there's another cycle. All right, that's 2 cycles, just like what I was saying earlier. And so there are times, like I'm saying, it didn't happen in this problem where you have to change. So a lot of time we default our interval from 0 to 2 pi. That means that we can just simply stay with this interval being start at 0. Okay, and then our interval here, our rotation here, will just end with that upper end here being 360. Okay, and then that's enough for one interval. I mean, for one complete rotation. One complete rotation. Okay, the rotation is this solid line angle opening up right there. Okay, see, one complete rotation, and that is usually enough to generate one graph. And we change our polar curves here. Okay, and then nothing else needs to be done. Nothing else needs to be changed. But then in other special case where you need to extend your interval, like I said earlier, to sort of like double, right? More like a symmetric interval. Then we just, you already know where to go. Okay, go here to the interval, click on that, change that lower end right here. All right, to your whatever specified destination, and then but make sure to also change this to double the amount or even triple, depending on what you need right there. All right. So now in that way, allow me to create another example where this time you are allowed it, and I am going to also use that decimal right there to just get the graph. We don't need to plot by hand, plot by points and plotting points anymore, but we're going to use the decimals activity that if you are a student who learn with me, you will have that link provided to you right there. But we're going to look into example 5. All right, and so now in example 5, let's, and we only need to have one problem here. Let's graph, and this time it's the same kind of problem. We're graphing, but we approach things completely differently. So we want to graph the polar equation R equals sine of 2 theta. Sine of 2 theta. And now let's graph this in an interval from 0 to 2 pi. And that interval is just good enough. And like I said, if you are in that position, that's why I give any of my students who learn with me this, the actual activity I created there, so that a lot of times on any of these graphs, you can spend your own time experiments more outside of those intervals I specified in the problem. So now we're going to use decimals. Okay, so here's this example. Here is about we use, or if you have some equivalent technologies, decimals is not the only thing. It's just for me in my shopping experience. Okay, in my experience for years I've been shopping for good technologies. I haven't found any good technology, but who knows, you are more successful than me in that. So basically here we use a graphing technology. Okay, but it takes a lot to describe the situation. So we use a graphing technology. Not decimals is not the only thing. So if you want to use decimals that I gave you with that link I gave you. The point now is that we use graphing technology not to just simply boom, here we go, here's the graph. We don't want that. We want to see the graph with the angle changes so that we can see where the graph is going from and going to. That's the idea. Okay, and so now in this way right here, then I'm going to switch over to decimals. Okay, and for anyone to kind of get a clear routine of how we use that. So the polar curve we are graphing here is sine of 2 theta. So I'm going to change that here. Sine of 2 theta. And that's the part where you can just type theta. Okay, and now the problem also said we want to graph that function sine of 2 theta in the interval from 0 to 2 pi. So that and also you understand from your trick understanding that this is just a one complete rotation. All right, so in that way, on my decimals, I'm going to swing over to interval. Okay, yes, lower end is 0, 0. It's already there, all set, all good. And then this is, we never have to change this. It will automatically be calculated for B. But now the end right here, since it's, like I said, the interval from 0 to 2 pi is only one rotation. So that means on decimals, we check with this rotation here. The ending of the rotation is at 360. That is a good check right here. So everything is all set. We turn that on. So if it was like this, that's off. We turn on the handle. If it was like this, it's off. We turn on that to really see the graph. Now we are ready to slide the slider. All right, so as we slide the slider, see, you can see that the angle is changing. And as the angle is changing, our radius, see, the point in green right here is indicating how the graph changes, and it makes some radius. Right? These are the polar points right here. It makes some radius as the angle changes. All right, and so as we changing, we have, all right, so we have one part of the graph done, right? By pi over 12, by pi over 2 right there. We have about one little loop of like a leaf looking, or like a flower looking shape like that. And then we're going to go further. Okay, and we come up to that. See, so now the negative radius, that's why the polar points go down to that part, went down to that part where it was dotted. Okay, and then, all right, so now we're about halfway of our complete rotation at 180 degrees. And then I'm going to slide this into even more. Okay, into even more of that. All right, and then this is the third leaf in our rose right here, in our flower, right? And then this is the last one right here. All right, and then through that you can learn, you can see, and we don't need table of values anymore. And with our rotation, we can see that where the negative radius has to be in whatever angle that is. Okay, and then we complete our loop here at 360 degrees. Okay, and so this is the picture of our polar equation R equals sine of 2 theta. Okay. All right, and so now that we are currently looking at and learning about polar equations in specifically, then a vital skill that needs to be learned here is that you need to learn how to convert an equation from the given polar format in the given polar coordinates representation into Cartesian equation like that. Okay, and so for example, see, like when we began talking about a polar equation, I was saying an equation like this, x squared plus y squared equals 5. Okay, an equation like this is regarded as a Cartesian equation where the x and the y variables are intended to represent the x value in the rectangular coordinates, and this is the y value in the rectangular coordinates, the horizontal and the vertical. But then what if you are given a polar equation like any of those you have seen earlier? Say r equals cosine of theta, for example. How do we write this one? How do we write something like this? This is a polar equation for now, for sure. You have seen that. I have given a lot of explanations. But now the vital skill we need to, is there a way that we can write this polar equation, this equation currently written as a polar equation, back into a Cartesian equation? Okay, so this is a Cartesian equation. This is polar equation. We want to learn that skill of how we specifically can convert or rewrite a polar equation back into a Cartesian equation. Now, I got to be clear. I'm not saying that this is the Cartesian equation for that. These are just any two random one. Okay, and now before we get into this problem, I have to say it takes some creativity. Okay, and it's such a limitless world out there of doing this, and you have to bring in as much algebra and as much trigonometry understandings of yours as much as possible. Okay, and so it will be impossible of me to deliver every kind of examples out there. Okay, and hopefully I'm bringing out hopefully a few, and then hopefully you can come up with some tips and tricks to pick it up on somewhere here and there from my examples, and then do your own problem. But then in the end, you have to depend completely on your own creativity and your own algebra background. Okay, and so at some point algebra is always an unavoidable thing. See, if you're taking class with me in a face-to-face, you will constantly hear me. You got to get your algebra going. Okay, all right. And so now I am going to get straight into example number 6 right here to continue from our last example. So here's example 6. Okay, so we want to write the Cartesian equation. Okay, write the Cartesian equation of the following polar equation. All right, so that means in this problem I am going to give you a few polar equations, and on each of these I am going to go through the steps to show you how we can write the given polar equation into Cartesian equation. So think as closely as the example 1 and 2 that we did, actually example 2 and 3 that we did earlier, where we had our polar points, okay, our points in polar coordinates and rewritten in Cartesian coordinates. Then it's the same here, but instead of being polar points, we're looking at polar equations. Okay, and that's the idea, but think as closely as that. So to remind anyone for here, and we have seen that in the earlier part of the lecture here already. So I just need to have a reminder. All we depend on is the following understanding. The horizontal rectangular coordinates is r times cosine theta. That's one relationship. And then the y, the vertical rectangular coordinates, is r times sine theta. That's another important relationship that we need to depend on. And then the last one here is r equals x squared plus y squared inside the square root, or alternatively you can think of that as r squared equals x squared plus y squared. Okay, there are other minor relationships, but these are the three most important ones that we will always depend on. Okay, so So I'm going to leave these here for a little while. So I'm going to use my other board for start putting up the different various problems like that. Okay, so now in our example 6 right here, let's look at part A. All right, so the first equation we have here in my lecture note I prepare for anyone. So how about r equals 4 cosine of theta? Okay, it's a polar curve. It's a polar equation. We want to rewrite this in terms of x and y, or u and v, or s and t, whatever. But s and t, or x and y, or u and v are meant to be or intended to be in rectangular coordinates or Cartesian coordinates, and that's the idea right there. Okay, so now the point I see here is that, I mean, as an algebra, and so there's no general rule or anything like that. So it depends on experience and creativity right here. But I see that we have a cosine here, and then there's an r here. So this cosine here simply on this side here is missing out an r. Because why? I mean, why am I thinking of an r there? If we multiply this cosine theta with an r, then, and for now ignoring the 4 like that, then multiplying cosine theta with an r, we can have that substituted by an x. Okay, that's some algebra expression right there. I mean, some algebra experience right there. So that means I'm going to multiply both sides. Okay, I'm going to multiply both sides by r. So left side multiplying with another r, giving me r squared times 4 r times cosine theta. Sweet, we got what we needed. R times cosine theta. So this is now going to be x. That's how we defined that. That's how that relationship pointed out for us. So this now in the next step will become 4x. We're slowly getting there. All right, and we will start, and anyone watching this will start picking up a good trick here and there according to where I go. And then even further, a better gift, it's just we did that to serve our first purpose. And then consequently it led us into, hey, there's a good usefulness of this r square. R square is, according to this relationship, r square can always be understood as x squared plus y squared. Okay, and so r squared equals x squared plus y squared. So I can substitute r squared here by x squared plus y squared. Ladies and gentlemen, you have completed your first work right here. Okay, you have re-expressed that polar equation into a Cartesian equation. This is the Cartesian equation. So sometimes it looks challenging at first, but throwing in a few algebra things, I highly recommend to be positive. Anyone's learning math with me right here, I always encourage you to be positive in your work. It may turn out wrong now. Scratch out your work, do a different way right there. That's how we can become a successful mathematician. Okay, do not be afraid of challenges. And when we're doing this, we have to face some challenge so that we can learn better and become better shaped at this kind of problem. Okay, so anything that, in my belief right here, anything that you put more efforts and time into it, you will keep getting better. Okay, and so that's the Cartesian equation for this. And once you got the point now is that once we've come to Cartesian equation, a good checkpoint for you to know whether you have successfully done with your problem. No more r and theta, only x and y left over. This is where you're done. And once you got to that point, you can put all your terms on one side, or you can just rearrange your equations. But as long as you only have x and y only, no more r and theta, you're good to go. That's your final answer. Okay, so that's one problem down right there. It seems short, but for anyone beginning into the work here, if it takes you some too much amount of time, that's okay. It's the way it is. Okay, I mean, look at my case right here. Now I'm teaching here in front of the camera. I've been doing this for over 20 years. Okay, since the first day I was taught with this kind of stuff. It's so many years of experience. But now, if you are this is your first time doing this, well, you don't blame yourself that why it takes so much time. Okay, but that's how we learn. All right, so let's head out into another one. So now we're done with the first one. So what about another one? So how about r equals 4 over 1 minus 3 sine theta? Okay. r equals 4 over 1 minus 3 sine theta. Okay, so now in what I see here, well, if we try one thing doesn't work, we try another one. So allow me to suggest, and also before I lecture, before I stand in front of the camera, I also do my own scratch work on any of these too. So allow me to show you what I found, the way that worked for me, and then you can also have your own creativity. But algebraically, this is what I did when I was going through the scratch work before the camera right here. I'm going to multiply that denominator to the left-hand side. So it gives me r times 1 minus 3 sine theta. Okay, I'm not doing magic. Like I said, before I stand in front of the camera here to teach, I had to spend time doing these problems on my own. There are problems that you can go teaching improvise, but there are problems you have to carefully prepare. Okay, so I just want to point out, when it comes to creativity, I'm just like anybody else. Okay, now I'm going to multiply the r through. Okay, so that gets me r minus 3 r sine theta. Okay, equals 4. All right, and so we having something like that. And so now I start recognizing this here is an x. Now excluding that r, excluding that 3, aside from that 3, r times sine theta, I might have accidentally set x, but this is actually y. Because of this relationship. Anytime we're looking at r times sine theta, that is our y variable. We can legally substitute that expression by y, for y. Okay, so now in that way, back to this equation. So I'm going to be at r minus 3 y equals 4. I'm almost done. I'm almost done. But I know I'm not done. I'm only almost done, but I'm not done. Why is that? Because we still have that r variable, that polar variable still here. So we have to completely get rid of that. Okay? But now good thing is it's only a one single variable there for that. So why don't we? But now I'm saying why don't we? When I was working it on before the camera here, when I was working it on my own, I had to try a lot of different ways. Surprisingly, on one simple step. We can now add this to the other side. Okay, so now it gives me r equals 4 plus 3y. 4 plus 3y. Okay, 4 plus 3y. And then now, and then I can, all right, and then from there, and then from that point on, I am going to square both sides. I'm going to square both sides. And like I said, when it was me before the camera here, I had to do a lot in each of these little steps there. Okay, and then now I'm going to square both sides. So I'm basically on any problem here, I'm just sharing what I have found. And then when you're on your own problem, doing your own. And on your own to do your own problem right there, then you're going to start exploring your own creativity. So now I'm going to square both sides here. So we have r squared to equal 4 plus 3y r squared. Okay, 4 plus 3y r squared. So that's still in terms of the Cartesian variables. But that one here, we're even closer. R squared, R squared, R squared, R squared. R squared equals x squared plus y squared. Okay, r squared equals x squared plus y squared. So now it's a perfect substitution for that. Okay, so x squared plus y squared equals 4 plus 3y r squared. Now as far as getting the Cartesian equation, we're done. We're done again. Okay, but now maybe a little bit simplification would be good. So something like that, completely okay now. Okay, you got your Cartesian equation completely nailed down because you have washed away all the r and theta variables already. Okay, but now let's see a little further. Why don't we FOIL out that square right here? So x squared plus y squared on the left hand side is here. That equals, this foiling out right here, think of that as a 4 plus 3y times 4 plus 3y's again. Multiplying that out, we're looking at 16 plus, right? And then that's 24y plus 9y squared. You can always double check me with my foiling work as well. Okay, So that's just, after I FOIL out the two identical factors, right, and combine like terms and all that. All right, but now 9y squared will cancel with one of that 9 squared right here. So we come up with a little bit of a nicer equation right here. So I'm looking at, how about, and I'm going to bring all terms to one side. So x squared, okay, minus 8y squared. See, x squared, those two cancel, minus 8y squared. I'm going to subtract 24y, and then I'm going to subtract 16 and make that equal 0. That's another form, same equation, just a different expression like that. Okay. All right. So now we're seeing that forms. Okay. This is the Cartesian equation of this beginning problem. All right. Let's now look at part C, okay? And we have another polar equation, r equals 5. It's an equation, and it's quite simple. Sometimes a simple thing can be dangerous, okay? So now I have r equals 5. So here's how I see it. R equals 5, okay? R equals 5. So why don't we, and that was just one way I found before the camera, before I stand in front of the camera here. That's when I was working on Scratchwork myself. Okay, but you can also try a different approach. My approach here, why don't we square both sides? So I'm bringing that into r squared equals 25. Okay, r squared equals 25. It's a constant. Okay, and this is on r squared. That looks familiar. The r squared here equals x squared plus y squared. Okay, r squared equals x squared plus y squared. So in that way, all of a sudden we realize we have found a substitution for r squared. So here we're looking at x squared plus y squared equals 25. We found another Cartesian equation. It looks challenging at first, but sometimes one little step right there, all of a sudden it turned the situation completely different. And then it opens up a new step for us. Okay, so that's how we get to the part C right here. But once again, this is not the only way. Okay, this is not the only way. Now, once you're done, and it should arrive at the same equation, but it's not the only way how you approach like that. Okay, there's no one way. You can try your own creativity differently as well. Okay, and how about another one? So this next one here, and like I said, no instructor will be able to cover all kinds of problems out there. So tentatively, this is about the last one in this example 4 over here that I have for anyone learning with me. Okay, but here I'm looking at r squared times cosine of 2 theta equals 9. Equals 9. So what I see here is, well, we already had r squared, but hold on to that. Let's leave it there as r squared. Let's leave it there as r squared. I mean, technically someone can rush into, x squared plus y squared to substitute for this, but I decide to leave it there. The cosine of 2 theta. Do we know something from trigonometry? That's why, as I said earlier before we got into this example, you got to bring in as much algebra and as much trigonometry as possible. Okay? Cosine squared theta minus sine squared theta. This is cosine of 2 theta equal to cosine square minus sine square of theta. Okay, and all that there equals 9 on the right hand side. Okay, we didn't get anywhere yet. Okay, then I'm going to multiply the r squared to each side right here. To each term there. Okay, so now the first term becomes r squared, or how about allow me to write it like this: r times cosine theta r squared. That's what happened after we multiplying r squared with cosine squared. R squared I'm going to multiply with sine squared. So minus, allow me to write r sine theta r squared equals 9. And now what have we ended up for ourselves here? This inside the square is x. Okay, that r cosine theta. And then that part here inside the square, r times sine theta. Okay, inside the square. That is that's y variable. So now all together, putting the pieces together. Now I'm looking at my final equation here is an x squared minus y squared equals 9. And now again, I see that I'm done with this example, with this particular example, because as far as soon as I have or we have completely washed away the old variables, all the r and the theta in our equation, and we're done. And once our equation only left behind with x and y, or u and v, or the s or t, but those are meant to be the rectangular variables, then we're done. Okay, so this is our Cartesian equation. Okay, so all right, so a little bit about why this skill is so vital. This skill that you are able to convert an equation from given polar equation to Cartesian equation. Why is that skill so vital? So particularly it is good when you are doing in a graphing situation again. Sometimes we will be working with polar curves that are a little challenging. So being able to change the polar curve into the Cartesian equation, we have a way to verify ourselves with that. And also some technology is not able to handle, some technology does not come with that capability to handle polar curves. To graph polar curves like that, then we can convert our equation from polar equation into the Cartesian equation and then use that for graphing. So for example, let me now quickly bring you into my Desmos browser. Okay, on my web browser right here with Desmos. So here. All right, so now let's say, to demonstrate the idea, the first, in part A, we did r equals 4 cosine theta. Okay, and then it was a graph like this, and in polar coordinates. It looks like that. Okay, but then in the end, it is just polar coordinates. It's just or rectangular. It's just a way to represent the point. But in the end, the curve itself is the curve. The curve is the curve. The physical curve is the physical curve. Just because we change to different representation doesn't mean it's going to change the shape of the curve. And so in that way, now I'm gonna. So this is the same curve in polar coordinates, and then it's a circle that we saw it according to the graph that Desmos gave us. But now in rectangular coordinates, okay, I'm going to hide that curve that we have found away. But we found in our math work earlier, in our algebraic work earlier, we found that this same polar curve has has Cartesian equation x squared plus y squared equals 4x. This graph in blue is now a Cartesian equation, okay, and it gives us a circle. It gives us a circle. And so let's look at the other graph. I'm hiding this graph away and the other graph. So now really it's just the same graph being in different colors. So the blue color is the Cartesian equation. So same graph, same curve, it's written in Cartesian equation. And then same graph, but now written in polar equation, expressed in polar coordinates. That's all there is. Okay, so just like that, in our part B of the example, I had r equals 4 over 1 minus 3 sine theta. Okay, and so that was the curve. That was the curve. So this was the curve that generated when our equation was a polar equation, okay? And then in polar coordinates, see, the graph won't even move. It's just we change a different way of representing every single point on this graph right here, okay? But now I'm gonna switch back to the regular rectangular coordinates, and now this is not the equation for that. We found that equation in our part B of the example, x squared minus 8y squared minus 24y minus 16 equals 0. Okay, so now I'm going to hide this away and I'm going to turn on this blue version, and it's still that exact same curve. Okay, the blue and the red. Okay, the red and now the blue. Right? The two are exactly the same curve. It's just different representation of the curve. Or just like that, what about when we were in part B? In part C right here, we had r equals 5. Okay, so now in polar coordinates, that was our curve in polar coordinates. Okay, and let me switch thing over to polar coordinates. Okay, it's a circle with radius 5, center at the pole, at the origin. And now back to rectangular coordinates. Okay, I'm going to change this to the equation we found was x squared plus y squared equals 25. And ladies and gentlemen, this was the equation for that same circle right there. So now red version was for polar coordinates, blue version is for rectangular coordinates, but they are the same graph. Okay, and same way, just like that, we can use for our r squared, for our last problem in example 6 right here is r squared times cosine of 2 theta. Okay, equals 9. And see, Desmos is not strong enough to do this, so I'm going to have to write this as cosine 2 theta. Okay, Desmos can only recognize linear r right there. Okay, so every technology has a limitation, but now this is the graph for that. Okay, so that's the graph for so we started out with r squared times cosine of 2 theta equals 9, but now I have to take square root on both sides there, and this is the graph that it gives me. So now let's look at the blue version. So I came to x squared, okay, minus y squared equals 9 right there. Okay, so let's see what the blue graph looks like. And the blue graph is exactly the same as the red graph that we've had earlier. All right, and so once again, that clears up the idea about, you know, why. I mean, it's one reason why we need to know how to convert an equation from polar coordinates into Cartesian coordinates, simply because a lot of times we need to verify whether or not our graphing device has given us the correct the graph for a polar curve like that. Okay, and then there could also be the cases where, you know, your graphing device, your graphing technology does not come with the capability to graph your polar equation. So being able to convert a polar equation to a Cartesian equation will help the big time, right, into getting the graphs of that polar curve. Okay, but that's just only one example of why it's good to know this skill that we're learning right there. Okay.